Okay, I'll start. Yeah, so hello everyone. So nice to meet you all. So nice to see you here. My name is Lior Bondarevsky. It's been a while. I've been 10 years in the cybersecurity industry, and then part of it in the IDF, in the Israeli army, and then in a company named Sentinel-1, if some of you are familiar with. And then I've joined this amazing project, an amazing network called the Secret Network. I'm not sure how many of you are familiar with, actually, who is familiar with Secret Network? Nice. We'll cover some of the things. Don't worry about it. I have one request. It's a workshop. It's not a presentation that you need to ask questions inside in an application. Feel free to ask everything you want, anytime you want. If there is something you don't know, something you do not understand, please feel free to ask, because the other slides are all based on the previous ones. Okay, so let's talk about the agenda of the workshop. So we'll start briefly to talk about the Secret Network, about the secret contracts. We're assuming you guys are familiar with Cosmos contracts. If not, we can cover it quickly. And then afterwards, we're gonna write some code. The way we're gonna write code is, we have Eshel here, who is also a dev. We're both devs in Secret. And then we're gonna write some code. We're gonna implement one of the features in a rock, paper, scissors game. We'll start in a template of a rock, paper, scissors game. We'll go on. Believe me, it's gonna be fun. So the beginning will be a cover. If you guys have any questions, feel free to go, and let's start. Okay, so secret contracts. Secret contracts, if you look at them, they look almost exactly as Cosmos contracts, right? They're all written in Rust. They're all compiled to WASM code, same as Cosmos contracts. I think that the main difference is what is going on behind the scene. Behind the scene, this contract receives its data absolutely encrypted, right? We want to preserve privacy. That's the whole goal of Secret Network. How do we preserve privacy? By using encryption. So the user, when it sends data to the contract, it sends it privately, it sends it encrypted. And then the contract receives it. It already receives it decrypted, because we have the backstage code who will decrypt it, but it received it. And then it will write things to the state. And also here, it has to be encrypted, right? If I write something to the state, that means something to the customer, something to the one who sent the transaction. I can't write it plain text. He sent me something that is private for him. I have to write it in a private way, in an encrypted way. And then finally, the output will also be encrypted. The encryption is, of course, for the one who sent the input, right? So if I ask or send a specific input and then receive an answer, I expect the answer to be for me and only for me. Only I know how to decrypt it. Yeah, so that was my expectation when I joined Secret, and apparently it is what it is. And then let's go forward and see how it was implemented. Yeah, so actually before we dive into implementation, I want to really convince you, why do we need privacy? We had a talk previously that Guy talked on the stage. Talking after him, it's hard. He's good at what he's doing. And then, Guy is our CEO, by the way. And then the only thing that I can add on top of what Guy said is that you need to imagine a world, a Web 2 world, without HTTPS at all. Would you guys provide your credit card there? I guess not. If yes, so you're that public, but I guess not. And that's what I want to do. I want to provide HTTPS, like HTTPS mechanism to the Web3. Let's go next. Yeah. So let's have an example, right? Even before an example, let's see a graph. So we have here a user, then we have the contract, and on the side we have another person who really wants your data. And this data can be your credit card, And it can be just I don't know, a vote you voted in a private voting mechanism, okay? So in a public chain, the user creates a transaction, then it sends it to the contract set the state accordingly, and then this nice person can see everything, all around, like completely. Now let's look in a private way, as you can see is now said. Yeah, so me as a user, I create a transaction, I use an SDK that can wrap it and encrypt it, and then send it to a secret contract. So the secret contract knows how to decrypt things. It's hard, right? Because if we have the key plaintext on the hard drive, we did nothing, right? So keep in mind that in a few slides, we will need to solve it, okay? If you go outside this door and you do not know how we store this key, I did nothing here, right? Because if the key is plaintext, if the key is on the computer, a node runner can do everything he wants.
So, sorry, are you doing symmetric encryption?
Yeah, this is symmetric. Okay, so the contract decrypts and yeah, that's it. So let's go for an example, right? The name of the presentation was rock, paper, scissors, right? So let's go with rock, paper, scissors. Bob here wants to send his bet, which is rock, his choice is rock, and the contract will store that Bob has chosen rock, right? But the other person didn't play it. So all you need to do is to read the state, to see that Bob have chosen rock in this case, and then all you need to do is paper, right? He stole all of his money. We're playing with money here. Yeah, so that's why the evil guy here is kind of happy. And then let's look in the private section. Right, so Bob sends blah, 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 blah. It's encrypted. We do not know how to decrypt it. And then the contract decrypts it. He knows that Bob said that in game X he wants to play scissors in this case. And then it encrypts it back in order to put it in the state. The other player will play, in this case, paper, and then the result is exposed. Me, as a contract developer, I can choose whether I want to expose something as a public thing or whether I want to store it as a private thing. It's very important because like, I want everyone to know the result. Why not? The evil guy won here. Sorry, Bob won here. Cool. Let's go next.
So can I ask one
Yeah,
question?
sure.
There is private blockchain in there, right?
Yeah. We're talking about secret, yeah.
But private, it's still permissionless, right?
Yeah.
But you make it private with your own features.
Yeah. Right. So I told you, I want to protect you from the node runner, right? If a node runner can find the key and decrypt everything, I did nothing here. It's as easy as create a new node. It's permissionless. All of you can do it. Get the key, and that's it. So I really wanted to keep it as a secret, but you know, it's in our code. You can see it. So let's do it. Right. So the main key here called TEE. It's a trusted execution environment. Has anybody heard about Intel SGX? Amazing. So Intel SGX is an awesome hardware that Intel invented in order to run in a trusted environment. The way they do it is quite not simple. We can share it privately if you guys want to hear a little bit more. But here you need to trust me. You can run in a trusted way where the CPU guys cannot read any of the data that is written by the enclave. The enclave is the execution environment, right? Other enclaves cannot read the data that was written by our enclave. So basically, even if you want to create a new execution environment that is trusted, but it's trusted in your own way, you cannot do it. You can do it, but you cannot read our data, which is really important because we have the guarantee that our data keeps private. This is the main thing. We're a private chain. Yeah, so we decided not to speak that much about TEs. It's quite a hard thing to really go deep down in, but we do invite you, if you want to hear any more, come to our booth. We have a booth like in A3, it's called, in A3 section. Come and hear more. We can share a lot of data. We can sit like for a whole day and speak about TEs. Yeah, let's go next. Okay, so if some of you were in the previous talk, that guy were on stage, you heard about like VRF or random. So actually, what's amazing here is that privacy can be a building block. You can build plenty of things using privacy only. For example, random number generator, right? So the V in VRF is verified. You have to make sure that the whole chain created the same random number that can be verified by every validator and then can be passed to the contract. We're going to use it really soon. So let's look a little bit down and see how it is done. So in our case, the proposer, he creates a block, right? We all know that proposer creates a block. Inside of the block, we have this super random number generated inside the TEE. Enclave generated this random number. And this is the only one who generated it, right? Then we can encrypt it and send it to all of the other validators. The other validators can do one thing. They can validate that this number was created inside the TEE and was encrypted inside the TEE. That's all we need. No one can create this in enclave instead of us. And actually we won. We created a new number. All of the validators saw that we created this, our code created this, and it was encrypted by our key. And then they verify it, and it can be passed up to the contract. It's going to end questions so far. Amazing. Let's go next. Yeah, so secret network is a cool thing. If you build a new project that needs random, that needs privacy, I would have chosen secret network without any thought. But we do understand that there are some projects that are running on different networks and do need these features, right? So we have an amazing suite we call privacy as a service, which basically means we want to serve other chains with this private data. In this case, let's talk about randomness, right? We want other chains to be able to retrieve some random numbers from secret network. Those are on-chain random numbers, yeah? And use it however they want. So in order to do this, we have two concepts. One of them is really well known in Cosmos. It's called IBC. Do you guys know what's IBC? Raise your hand if you know. Where is it? Great. So IBC is inter-blockchain communication. Basically means me as a Cosmos blockchain can interact with other Cosmos blockchains and retrieve whatever data I want from them, right? So I can interact with a secret contract from Juno, retrieve data, and then use it however I want. But a new amazing thing that we're still implementing, it will be available in the next secret network upgrade, is GMPs. It's a feature that Axelar implemented, which called global message passing. Yeah, go ahead.
Just have a question about how the randomness works. For example, if you create the game rock, paper, scissors on Juno.
Yeah.
And so if you make the randomness, you play with a random player, for example.
Yeah.
The time there is the IBC query, can it possible to like intercept and check and play the right move?
Yeah, so it can be intercepted, but it's based on your development, right? So you can do, what basically you want to do is to have the random number being headed to you in an atomic way, right? So you can use replies, you can use some mechanisms that are implemented in Cosmos, in order to have such thing, right? If you get a timeout, so this is the main thing, right? I can sit on the relayer and choose not to give you the random number and wait until I get the best random number I can get, right? So you will get a timeout, right? You will get a timeout for your message, and then you as a developer need to choose whether you want treat timeout as an error and then give the money back, or treat timeout as a lose, right? So someone trying to intercept you. So it's still hard to be implemented like in the correct way just because of the relayers, because relayers can intercept the data. But you as a developer has the choice of how to do it right.
No, but even if the random number is given, but you can just read it as a middleman, as a relayer, or anyone?
Yeah, as a relay you can read it, right?
Even if it's shared, you just take the random number. I'm taking the example, for example, for NFTs.
Right.
And you want to get like a special numbers, or I don't know, for getting your NFT. Or
Right.
but you can, even if you intercept, okay, no.
Yeah, you shouldn't have the opportunity to read it before it was before the transaction made. But if you want, we can go through the details how to make it atomic. Right, this is the main thing. If you can make it atomic, you cannot intercept it. Right, so GMPs, global message passing. What it basically means is that EVMs cannot speak with Cosmos chains, right? Me as an EVM developer, as an EVM contract developer, I can write a contract that interacts with Cosmos contract and gets data from it. So imagine a thing like we had domestic calls using IBC, and then we have international calls using GMPs. So stay tuned. It should be posted real soon when the upgrade will be, and then as soon as we'll have the upgrade, we'll have GMPs ready for use.
You have light clients on both sides?
We do. All you need to do is to have a relayer on both sides. You have Axelar.
Okay, it's like a decentralized relay system where anyone
Yeah.
can run.
Yeah, that's what Axelar does, yeah. Let's go ahead. Okay, we're almost ready to start, right? So first of all, any questions so far? Cool. So, okay, we're gonna do it here. Actually, we'll write the code. But if you guys wanna start and do it alone, you are more than welcome. We have a QR code here that will lead you to a Gitpod. Gitpod is a platform implemented by GitHub, what basically means you can have an online Docker which runs the things. But if you want to hear how we do it and what do we do, what do we want to do, so you're more than welcome to stay with us and with the talk. So I'll let you guys have the ability to scan. Great. So let's start. I want to first to show you what do we have right now, right? We have a rock, paper, scissors game that is implemented as a 1v1 game. The same protocol as we've seen in the previous slide. So me as a person, I can create a new game. The other one can join the game. Then I can choose I don't know, my choice is paper, and then the other one can choose that his choice is rock. And let's see how it works, right? Right, so this is a UI. We are not UI people. I'm sorry about it. Like, we are far away from creating a good UI, but we're trying our best. You see, we have images, which is amazing for me. Thank you. I like it. Yeah, so we're using Kepler Wallet. We connected our wallet, and then we create a new game. I shall go ahead, create a new game, please. Nice. So we'll bet one whole secret. No, don't worry, it's a dev testnet. They don't trust me with real money. Right, so the game was created. We have a game code which is randomly generated. We'll see how. And then I'll send it to my friend. Come join me to this game. I shall apparently has a friend which is a browser. Cool, so I give myself a name, put a game code, and we'll bet one secret as well. I'm joining the game.
Oh, there's a pepper here.
Okay. Cool. Well, it take a while. Oh, amazing. So the game is started. Now I need to choose what do I want to bet. So let's go with who want to choose? Scissors. Right. So I'll give another person the opportunity to choose. Choose wisely. Take it to your screen. Yeah, this is the Kepler view of signing the transaction. Believe us, you're gonna press approve, right? Yeah. So the first player has submitted his choice, and then we are playing the third. We are waiting for the second player. Let's play. Who wanna choose? Rock.
Okay. So this one should win.
Yeah, should.
Yeah. Oh,
Take it to your side as well.
press approve.
Nice. You've done it correctly. You won. But I will tell you what. Like, this is already implemented. You saw it's working. We'll walk through the code just a bit, but I'll tell you what, like the next step of ours is to fix my problem. My problem is that I don't have any friends, right? So if I play with myself, I will win all the time, right? So I want to play this computer. In order to play versus computer, I need to generate a random number. A random number between 1 to 3, but a random number. Okay, so let's start viewing the code that we have so far.
Let's just show that this is not yet implemented, so we can implement. We have an incentive to implement it. So oops, this one is not yet implemented, so let's do it.
Yeah. So first, let's look at the code that we have so far. How many of you guys are familiar with Rust? Amazing, and with smart contracts on Cosmos in general? Okay, cool. So if you have any questions about the API, please let me know, because the API is going to be quite simple. We have 3 entry points. In Cosmos, we have more than 3, but we're going to look at 3 entry points in total. We have the instantiate entry points, which is called when you init a contract. Then we have the execute entry point, which is called on every transaction. And we have a query entry point, which is called for queries, right? So let's walk through the execute entry point. Let's look at the function itself.
The function itself?
Yeah, so we have the execute. Quite simple, the same as everyone. We have the depth, then we have the env, the information, and then we have the message itself, right? So I want to distinguish between 3 types of messages. We have a new game message, which we've seen just before, when you create a new game. Then we have a join game message, and we have submit choice message. Please ignore the play this computer. This is the one we will implement anytime soon. So let's start with a new game. Let's go to the function of a new game. Let's see how it works. Function, please. The one in execute rs. Right. Please double click on it just to see it in full screen.
This one?
Double click here. Right. Amazing. So we have the new game function. When we create a new game, we need to create a game code, right? We decided to make it randomly just for us not to keep any data in the state of the game ID, for others not be able to, I don't know, join my game without me sending them the game ID. So let's see how do we create a random game ID. Spoiler alert, we don't gonna use the VRF we just spoke about, right? We wanted to give another example of people implemented game random. Let's see how it does. Right, so.
Oh, sorry.
Oh, that's not this one.
Oh, this is the good one. This is the good one.
It was a bad spoiler, sorry.
Wait, this is the good one.
Yeah, go to the different branch.
I'm gonna find it myself here.
Right, so what people basically do in order to create a random on other chains, they have two choices. One of them, go off-chain, ask for a random from one of the oracles, and then go back and use this random, right? So off-chain, we have one big problem with off-chains. They are centralized. Being centralized means they can cheat us, right? We don't want it. So the off-chain idea is off the topic here. So the other idea is to get the data from the block, like we have the height of the block, and then we have the sender, and we can manipulate the data in order to get the random number, right? We create an entropy from which we will create a random number. Yeah, so we have the height, which is quite known by everyone, and we have the sender, which is known by everyone. So we have two things that are known by everyone and can be predicted. Predictable random is not always a bad thing. Here it's not that bad. But when we deal with money, when we deal with actual things, we cannot have predictable random, right? Imagine a roulette game that if you've seen in our booth, we present a roulette game. Imagine a roulette game with predictable money, with predictable random, sorry. Means you can steal all of our money. Right, so let's go ahead. As you can see here, we created a new random. We converted it to a string people can read. That's it. Let's go back. Any questions so far? Right. Let's go back to contract RS. Right, amazing. So let's view real quickly the join game. I think the new game, we covered the main thing in new game. Let's review the join game. Let's see, what time is it? Nice. Join game. So me as a player, I want to join an existing game. I need to provide the player name and the game ID, right? It's the same thing we done in the UI. Right, so we'll load from the store the data. Here it doesn't really matter if the data is plain text, not plain text. People can read it. And then we just do a sanity check and we update ourselves as the second player, right? Okay, those two transactions were nice, but let's see the real deal. How do we handle the real mechanism of storing private data? So let's go to the choices. It's in contracts RS back. Right, so submit choice. Me as a player, I'm already as part of a part of this game. I want to submit my choice. Okay, so if I want to submit my choice, I'm gonna load the match info, okay, and update my choice in the match info, right? But okay, let's see that I'm really updating the choice. Yeah, loading the match info is basically loading from a store, nothing that special. But let's see how do we update the choice. So go a little bit down. Sanity check here, and then we set our choice, right? But, okay, if I can load the match info, basically means that we have a storage in which we have a match info, right? If I'm the second player to play, I can load the match info on my end, on my node, read what you chose, and then choose the one that wins, right? The same as we done with the rock. So here it's quite harder. If you will see, we saw the load match info before. If you will see the load match info, it looks the same as in every Cosmos chain. We load from a store, but the store is encrypted. The backscene of secret network actually decrypts the data for us because we are the contract, we are running as part of this amazing TEE we spoke about, and we can read the data. We can read only our data as a contract, right? So we are setting the choice for a player, and then nothing that special. We're gonna set the data in the state, and then let's look down and we'll see that we are handling a case when our state is done, right? When the second player submitted his choice, we can split the rewards, right? So, yeah, nothing that special, right? I read from the DB the first choice. Then I check who the winner is based on both choices. And then I split the rewards and add, let's go downstairs. Yeah, I add a debug, which debug means basically plain text message with the winner identity. Right. Any questions about the implementation of 1v1? Yeah, go ahead.
Is the outcome is decided in the second transaction of the second player?
Yeah, correct.
Also, the rewards are.
The rewards are given to the one who won.
Okay, so there could be. Okay, so if the outcome is known in the second transaction, can it be interacted with a smart contract?
With which smart contract?
So I can write a smart contract which will send the I'm a second player and I will send my transaction through the smart contract and it will send, for example, scissors.
Yeah.
And at the end of the transaction, if I see that I don't have money
Yeah.
received, I will revert, right?
Yeah. So you are talking about an attack that you'll be based on the revert state of the Cosmos chain. That if submessage failed, so everything is reverted. We have a solution for it. It's an amazing question, right? Because we have a thing, we've thought about it completely, and we didn't have a solution quite a while. And then the solution was quite simple. The solution was to add a specific sub-message. We call it last message indicator. I don't remember the full name. We can check it up. Right, and you as a contract developer can absolutely say that you only add this message, you only do this transaction if you are the last message in the block. So you as a contract cannot intercept with the result anymore. Because if you added a sub-message, right, and you called another contract, this contract said this is the last message in the block. We in the chain check if it wasn't the last message in the block, and we do not hand the result to the previous contract. So you do not know if he won, he lost, whatsoever.
Okay,
Right.
and if I understand correctly, the MBB is not possible on Secret, right? Or is it possible? Parallel MBB?
We need to discuss it a little bit more. It's not a simple question of a yes, no. Yeah, let's discuss it in a bit, okay?
And that block and random value that you get.
We didn't use it yet.
Okay.
Cool. We will use it very soon. Yeah.
So you were saying that what is the routine that disables the fact that the computer may see the response, the submitted response of this user?
Right. Right. So.
Have you shown it?
Yeah, I can repeat it for sure. Like, the result here looks plaintext for me, right? The contract will read plaintext. The backstage of Secret will then encrypt the result in a way that no one can know what the result is, right? So the only thing we need to do is to protect the key that encrypts the result. So in this case, the key is very simple. The key is the public key of the user that we send him the data for, right? So if we have the public key of the user, we can encrypt it with the public key of the user, and then the user can use its own private key in order to decrypt it, right? So yeah, that's what I meant when I said the contract cannot see it. Any other questions?
So the beautiful thing is that you don't have to develop with that in mind. You just save stuff to the storage, and then it is saved encrypted. You
Okay,
can
so
rely.
you don't say which data should be encrypted. Every data that comes from the contract is automatic.
By default, everything encrypted. If you want something to be plaintext, you can ask for it. We have another example of a even nicer way to use a plaintext data, but by default, everything is encrypted. Okay? Yeah, go ahead.
Just something you mentioned made me think. Is there no forward secrecy for transaction responses? Is that the case, since they're encrypted for the public key?
Sorry, can you repeat it?
So like forward secrecy, if my key pair is compromised,
Yeah.
the person who compromises my key can look through history at my transaction.
Yeah, if you have your key, yeah, it's a bad thing. But you need to understand that only if the contract will give you the information, right? If you have the needed query in order to, right? It cannot read the state of the contract. But yeah, we actually have a mechanism we call, we have two mechanisms. One of them is called viewing keys, which basically means if I want to give you a permission to view my things, I can provide you with a viewing key, which is a blob I signed with my key. And then if you provide this viewing key to the contract, it will let you see the information I wanted to share with you. And then we have even better mechanism, because creating a viewing key is actually accessing the contract, creating a transaction. It's quite expensive with gas. And then we have another way, which is called permit, which basically means I use my wallet and only my wallet to create a blob, to encrypt it, and then the blob contains who I give the permission for and what type of permission, and of course date of expiry, like everything around.
Okay, so like a little ACL that you can embed.
Yeah.
Just to understand the
Yeah.
architecture, the computer will also submit the same way a user submits the response, or is it another way?
I'm not sure what do you mean by the same computer.
The computer, now we are having the use case where we have a person and competing with the computer.
Yeah.
Which randomized data.
Right.
So the program,
Yeah.
the computer, will submit through this contract also.
Yeah, the contract will be implemented with the computer choice. We'll see just in a bit.
So it's completely different.
It's
contract for
kind of different. It will be the same contract,
so it's
completely the same. Yeah, we didn't see the code yet. We didn't see it.
The same contract that has two interfaces, one for playing 1 versus 1, and in a little bit we will add the interface to playing versus the computer. So this one we didn't show yet.
Okay, because I thought that the computer will also use the same contract for the game in order to submit.
Yeah, the contract here, it do not need to send a transaction to himself in order to submit his choice. All you need to do is like to run the code that is needed in order to submit the choice. But as soon as we'll have the first choice, we just need to calculate the second choice, round things up, and go ahead, right? Right.
We will add another message to the same contract, but we will add it in the future.
Yeah. Any other questions? Cool. So let's do some cyber. Let's do some code. Amazing. So, okay, do you have it? Do you have it ready?
Yeah.
Yeah. Cool. Amazing.
So now we want to go over the code of the versus computer, right?
We want to implement it. Yeah.
Okay. So it's already implemented. So we can
Yeah.
yeah.
But it's commented out. Should be. It's not commented out. Okay. So, okay. Cool. Amazing. You're right. Cool. So we have here a new message. The message called play versus computer, right? What do we want to do? We want to submit our choice and then let the computer to choose randomly his choice and to choose the winner, right? If the random is not accurate, the computer might be always the winner, right? If the contract wants to win, it can win 100% of the times, right? So we have to prove you that we use a random number. The same random number we generated by the chain, right? So the random number that was generated by the chain is actually generated for every block and for every contract. So in the same block, all of the different contracts will receive different random numbers. How do we do it? Is by simply injecting the execution ID of the specific contract to the random generation, right? We can generate the random based on the random number we created by the block, and then inject the execution ID, create a new random number for the specific contract. Right. So let's implement or see the implementation of playing with computer. Okay. Right. Guys, we have 3 words here. 3 words that says random number, right? Random number are 2 words, but here we only need to use 1 more word to have a random number. We access the environment. The environment is the main thing that is controlled by the backstage of the network. Every custom network creates environment. Our environment has the block. Inside the block, we have random blob. That's all you need. You got a verified random number using 3 words and 2 dots. Right. You can see the unwrap here. So if we look into the random, we'll see that it's optional. Why was it optional? Somehow it can't be created, right, on previous versions of the chain, right? So in case of the random not being created, this one, will be none. Here,
It's none for queries. Right?
yeah. Here, it's none for queries, for example. Yeah, it's a good example, right? Here, we're certain that the random number is created. We know on what version we are running on. And we know that this one will absolutely be something. Okay, so we'll access the random number. We'll get the first byte. We don't need any more. We just need a number between 1 to 3. We don't need any enormous numbers. And then,
It's 32 bytes. So
yeah.
So we'll take only the first one.
We'll take the first byte. In this case, we'll computer choice. Right. We'll do the from number. From number is quite a simple function. Just do modulo 3 and chooses the results, right? But I want to speak about 2 other ideas of how to implement it. First one, let's use the OS random. Let's use the random that the operating system gives us. Way easier, 2 words, 1 dot. Sounds easier. Do you guys agree with me? Okay, so let's do it. Okay, actually, let's change it up. Okay, I have one big problem with the OS random. We're a blockchain, right? We have to be synchronized with all the nodes, right? So when we create a block, the main thing that is going on after the block creation is calculating what we call app hash, application hash. Applied hash? Is it applied hash? Yeah. Right, so we calculate app hash. Now, the consensus, they're all like these amazing words that means we're synchronized, won't be if we will use the OS random. I'll get 2, Eshel here will get 5, and the other people will get 6 and 7 and 8. Will be messed up, we won't reach consensus. Right, so OS random cannot be used. Okay, so the other thing we can use, we can do the same thing we done with the game ID, right? We can use the other environmental things in the block, such as its height and the sender, or even the block hash, right? We can use all of them to create an entropy and then create a random number. Cool with you? Right. It might be working, but it can be anticipated, right? You can know beforehand, you as a validator who creates the block can know beforehand what will be the random number. It's cool, but you will have enemies. We don't want enemies. We don't love enemies. Right. So after thinking of all of these things, I would compromise and use 3 words, 2 dots, in order to get on-chain random. Right. So we have this new contract we implemented, which is a roulette that is running on-chain. We have an example on my computer there. If you want, you can join me afterwards, and I will show you. Then I had a conversation with a friend of mine. He's a gambler. He gambles online. He loves it. But the thing he hates the most is the casino. He can't trust the casino. Believe me, guys, I've been 10 years in the cybersecurity industry. You can't trust centralized things. They can manipulate you so easily. They can show you one code sample and run 10 other code samples. They can do everything they want in order to make you happy, but they make you way sad than you think you are, right? So here we have verified, proven random number. Right, so let's go ahead just to see the continuation of things. So we use the same function we used before. We already have the computer choice. Then we calculate the winner. Based on the result, we print who was the winner. And then we do something that is called like add attribute plaintext. Right, so in Cosmos, when you have a result, you have such things called event, right? So you have a structure that basically means what happened during the calculation or during the compute of this amazing transaction, right? So as I said, by default, all of the things are encrypted. Both the events and the attributes, which are a part of the event, are encrypted. Yet I can choose, as a contract developer, I can choose to add a plain text attribute here, and then to share with you guys what was the computer choice. Something happened here. Yeah, to share with you guys what was the computer choice and then what was the result. The UI can look at those attributes and understand what he wants to show you based on those attributes. Right. So basically that's it. We actually had it in half of the time. So I really want to discuss with you guys, what do you think? Have you had the opportunity to write something on Secret Network? Have you had any struggles, anything we can discuss about? Feel free.
Maybe we can show the result of the
Yeah, sure. Let's solve the
So this one is the old one. So I'll just refresh. No way. So there's a Git pod environment that you two can work with. That's the one that was with the QR. If anybody tried. So there's a server that we can run from there, and you get the UI. So I will run it right now, so you can see. Oh, although we have to build and deploy the contract. Do you want to show that?
Yeah, let's do it. Let's build the contract, the same as you do in other Cosmos chains. Let's do it.
So do you want to explain the steps for deploying the contract, like with the store step and the instantiate step?
We'll do it as soon as you will do it yourself, yeah.
We already compiled the contract. So
you're starting in? Okay, cool. So the first thing you need to do is upload your contract to the chain, right? You need to upload your code base to the chain. So the way you do it is, here we have like a makefile that do it, but of course you can do it using your CLI or your, I don't know, Secret.js, for example. What we basically do is we store the contract, as you can see here, we store the contract, we set the gas limit, and then we just put it together and receive the transaction hash. Right, so let's initialize the contract. As I've said before, we have the instantiate function, the function that will be called once we initiate the contract. Let's do it.
Yeah, I just did it.
Oh, sorry. Yeah, so we call the instantiate. It's the same as in other Cosmos chains. It shouldn't be surprising for you if you are familiar with Cosmos contracts. Right, and now that the contract is there, it's instantiated already, we can send transactions. So let's have the UI.
Oh yeah, we have to run it.
Actually, it's using the same link we had in the QR code. So you are free to use it whenever you want, however you like. Feel free to use it. Nice. So we need to connect your wallet first. You need to use Kepler wallet in this case. Amazing. And then instead of creating a new game, we'll play versus the computer. previously we saw that the feature wasn't implemented yet, and then the computer, we had a tie. I never win, by the way.
Actually, I win quite a lot. Let's try again. I'm approving all of these transactions right here. Because if it wasn't included.
Amazing, you won.
I told you this,
I would have chosen paper 100%, like, okay. Right, so it is what it is. We as developers don't have any access to this random. We do not have access to any of the keys. It's an amazing thing that works by himself without us interfering. And yeah, it's your time for questions, for any struggles. Yeah.
Quick question.
Yeah.
I'm not a coder, so
Feel
I wasn't
free.
too lost, so congrats.
Thank you.
Is there any notion of seed to generate randomness, and how does it work?
Right, so in order to be absolutely synchronized, there's this thing called seed, right? That it's a small, kind of small entropy, which you use as part of your PRNG in order to create new random numbers, right? So you can have, for example, 32 bytes of a seed that will create you 100 or 2,000 bytes of random numbers, right? But there's one big issue here. If you share your seed with others, I can anticipate what will be the next random number and the next 10,000 random numbers, right? So this is the main thing that the other chain is afraid of, right? If you create a seed, let's say you got a seed from Secret Network or from an off-chain service. You store the seed in your store, you lost the game. I can see your seed, I can use it however I want, and I will win your game 100% of the times, right? So yeah, you have a seed. We also have the mechanism to use the random number we generate as a seed. You can use it as a seed, but in our case, it is stored privately on your store. Right. Any other questions? Go ahead.
You said that validator doesn't have access to random. They cannot know the random number, right? Is it possible for them to simulate on state? Like to put some transaction to simulate like something interacting with the state, and so they can know the output of this transaction?
You mean by forking the chain in order, right? It's a good, you had a good question here as well. Yeah, we didn't touch that much of how we implement the random, but what basically we want to do is we want to, of course, protect ourselves from fork attacks, right? Because if I can fork the chain, me as a validator, I can have a contract that receives this number, prints it plain text on the screen, and then go to the real chain and do whatever I want. Right, it's an amazing question. So in order to fix this problem, we actually have the entire validator set being a part of the random number. So when we generate a random number, we use 3 things in total, even 4. One of them is a random number generated by an SGX. As simple as that, you as an OS operator might be interfering with this number, right? The second thing is a key that is stored inside the SGX. Okay, this is the second key. So we protect ourselves from the OS. The third one is the whole validator set. So when you're forking the network, the validator set will include only you, right? You cannot, it's impossible to ask all of the validators, please join me to a fork, let's rule secret network, right? Because if you do it, you actually have everything going on, you can do whatever you want, right? So the whole validator set is being concatenated to the random number, right? So when forked, the random number will be different, in like completely different.
And if you know the outcome of the state after the block, like when you validate the block, you already know the outcome, right? Like also
Yeah, but the outcome is encrypted. Yeah, you cannot know if the outcome means win, the outcome means lose, the outcome is encrypted.
Yeah, you don't know outcome.
Yeah.
But state is fixed like in a simulation, right? So what if I will input the next transaction into this block? Like, will it change the outcome or not?
I'm not sure I understand the question.
So you have a fixed transaction in the block, right?
Right,
So and they will change a state in a certain way, right?
right.
And if I will input like transaction above which doesn't exist, like, and I will like input, for example, my transaction with some kind of transfer, because there's output, someone will get money, right? And I can actually simulate and input different transaction which actually doesn't interact with any smart contract, but will
Right.
just include one transfer of money from A to B.
Right.
It doesn't have money. Actually, it makes, and I will know the outcome, right?
Yeah, but it's the same problem we spoke about previously, right? You can put the last message, and it will be the last message in the block, right? You can't do anything after this message.
Okay. So
Not even sending money from one to another.
last message in the block means that it must be like the.
Must be the last message. If not, it will fail no matter what.
Doesn't that constrain the transaction throughput very much?
It is, but
So you can basically have one action per block.
it depends on how it was built, right? If all of the transactions came before these transactions, so no. But yeah, if it's the first transaction, it might be the last transaction. It might interfere, but we're talking money. Like there is no other way, or we couldn't think of other way to solve this issue. And this issue is quite a simple way to attack, and quite a good attack, right? You can anticipate the result. You can know what was the result. It's basically like you can see private data. We don't want you to be able to do it. So yeah, you as a contract developer has the ability to choose that your transaction will be the last. Me as a user, I can choose not to use your contracts if I see that it will be, I don't know, interfering with the blocks.
But I can make like a no-op contract and enforce that it's the last thing, and then just pay to run it every block, essentially.
Yeah, you can. We need to trust some of the contract developers.
One way to solve it would be to require those kind of transactions to pay a higher fee,
Yeah.
because there is only one place to put them in the block.
Right. As a contract developer, you can run an infinite loop or some loop that, I don't know, infinite doesn't matter because you have gas, but you can fill all of the gas, and therefore the block will be used only for your transaction as well.
So instead of interacting with the rock, paper, scissors game as a wallet, what if I wrapped it in another contract where if it calls out to make the choice and it doesn't get a response that it won, it errors, reverting the contract. So
Wait, repeat it, sorry.
basically, I have a smart contract
Yeah.
that submits an option of the game. If it doesn't win, it throws an error, reverting the transaction.
It's the same case as before.
Yeah, it's the same case. If it's like the last transaction, you can throw an error.
The way to solve it is to put in the contract that these only accept transactions that are the last in the block, and then you can
Yeah.
you
Actually,
can
the
add
first-
more messages after that.
The first thing I've done on Secret Network, like the first thing was creating a blackjack game. Like we had a thing to create something new that uses features from Secret Network. So I created a blackjack game, and we found this issue on the blackjack game when we tried to attack it, and then we came with the solution.
So I guess for the last block thing, you could basically just charge a gas fee proportional
Yeah.
to what filling the rest of the block
Yeah,
would cost.
you
and
can.
just make it very expensive.
Yeah.
And we can order it to be the last one to minimize the interference.
Yeah.
Right. Any other questions?
Well, I might have one question. So I think I'm not, quite clear on the trusted execution environment, because also I'm, in your site and here you say there's a hardware requirement for the proposer node. Does this mean that our transaction go through some specific node that has to calculate all these keys and
Yeah.
does the encryption? So that means that we need to have that hardware as a validator or as a node.
No, so actually
how does this flow? So
every node has to have Intel SGX as an hardware. Every node.
That's an assumption, right?
Yeah, that's an assumption. You cannot run secret node without having Intel SGX. It's not that hard as it seems to be, right? You can pay a little bit more to Azure in order to have such thing, and all the other cloud providers support it as well. Not as AWS, but all that.
So basically, okay, we have the proposer node, I mean TEE. So it is doing symmetric encryption. So and it has the key, in the hardware, right, at some point. And so which basically acts like an API when saving and submitting transactions, or maybe submitting the results.
Right.
So and the smart contracts are actually sending data through that TE environment. So that's how the smart contracts and the third-party developers do not have any access to the key. So this is how it works. Right?
Yeah, the smart contract is running as an enclave inside this SGX environment, right? So he's the one who has access to the key and everything around.
So and the validators and no malicious node can play around with that TE code before they spin up the node. So
You cannot play with the TE code because the TE code is signed and validated by Intel. So when I interact with another node, I validate that the code is running has the same hash as the code I'm running. Right?
You said that you calculate a new random number for every
Block.
contract.
For every block, for every contract.
Every block, every contract. It seems expensive.
No, it's not quite expensive because the random number is generated for every block in general. And then to make it special for every contract, all I need to do is concatenate it with the execution ID of the contract and then hash it back. Right? So hash means you cannot revert the hash and you cannot know what was the base number, and then it's all I need to do. So it's as simple as hashing.
Where in the actual transaction flow does that happen?
In Tendermint.
In Tendermint.
In Tendermint. We have had to change Tendermint in order to do it.
So you have your implementation of NL, right? So
We have an own implementation of Tendermint, we have our own implementation of Cosmos, and of course an own implementation of Cos and Wasm.
yeah, so they're in your GitHub, right?
Yeah. Any other questions?
All good on my side, thank you.
Amazing. It was so nice to meet you. Really, I enjoyed this part a lot. Please feel free to approach us. Yeah.
Just a random question. Is there any way to export that randomness to other chains?
Yeah, for sure. We talked about it. You can export it both by using IBC, and then if you want to export it to EVMs, you can use GMPs, which is Axelar feature, to intercommunicate between EVM chains and Cosmos chains.
So your custom chain also compatible with ABC?
Yeah. Right. It was really nice to be here, guys, and please feel free to approach. If you want to connect on Telegram, feel free. Thank you so much.